So, all right, so let's begin with data compression. Claude Shannon had this quote from his paper, his landmark paper, about the fundamental problem of communication, which is that of reproducing at one point, either exactly or approximately a message selected at another point. So if we modify this quote just slightly, we can get what I think is basically the definition of data compression. If we replace communication with data compression, then the fundamental problem of data compression is that of reproducing at one point, either exactly or approximately a message selected at another point with a constraint that we want to use as few bits as possible. So the picture you should have in mind is something like this. So we have some sender, which is 0.8, that is trying to communicate or compress some message. And it does so with an encoder or an encoding algorithm and creates a bit stream. And we assume there's perfect transmission, so we don't lose the bits in this process. And then the decoder decodes this bit string back into the message at point B, so the receiver receives the original message. And this point A and point B, they don't have to be spatially separated, as in the case sort of between your laptop and you're trying to send a message to a Gmail server. They could also be temporally separated, right? So you could be compressing a file on your computer right now in 2021, and you want to look at the file in the future. So you're essentially transmitting this file to the future you in, say, 2 years later in 2023. So this is sort of the picture I want you to keep in mind when we talk about compression. So sort of this communication setup here. And let's begin with lossless compression. So this is trying to compress such that the receiver receives a perfect copy of the original message. So just to be a little bit more precise, we assume the data is a random variable x that takes value in a set, this calligraphic x. It's also called the alphabet. And it comes from some distribution P. And what we want to do is to develop what's called the code, or also you can just think of it as a lookup table that assigns a unique bit string to each outcome or value in this alphabet. So here's a visualization of what we're working with, which is a random variable that takes value in some set, each with a probability value. And what we want to come up with is what's called a code, basically an assignment to each value in the alphabet, a bit string, such that the encoder and decoder can just use this lookup table to convert symbols to the bit string and bit string back to the symbol. And the goal is to design the code such that the average code length, or the expected code length, it's also called bit rate in information theory jargon. We want this quantity to be as small as possible. So this is what we mean by compression, right? So we want to minimize this expected value of the code length. So here the code length is given by just counting the number of bits in each message for each bit string for each message. And turns out there's people work this out already. There's a theorem for what's the best you can do. So if you call the minimum expected code length possible, if you call this L star, then L star has to satisfy this inequality. So it has to be at least greater than or equal to the entropy of the source. And you can do pretty well. You can get actually really close to the entropy, such that your expected code length doesn't exceed 1 more than this entropy, where the entropy is defined as this in this equation here. So it's, again, some expected value. And the thing we're averaging over is this negative log probability, which you can think of as the amount of information in each observation of x. And it also turns out that we can actually achieve this limit by algorithms such as Huffman coding. So you may have seen this in your computer science class. So it's a fairly straightforward algorithm that builds a binary tree such that you want the different branches to have roughly equal probability. And you can just read off of this tree to get some kind of code. And amazingly, the code length for each symbol is roughly this negative log probability. So roughly the information content in each observation. And the code length of Huffman coding achieves this fundamental inequality. That is, we are very, very close to the entropy of the source. So the main message here is that once we know some discrete distribution, P of X, then we don't have to worry about how to develop a compression algorithm. So people have already worked out a way to optimally compress the observations from this distribution with algorithms such as Huffman coding. And again, this entropy is sort of the fundamental limit of lossless compression. Now, previously, we've assumed we know this distribution, the source distribution. So again, it's this table of values. But what if we don't know the distribution? Now, the common scenario is we have sample access to this distribution. So we have IID samples, and a straightforward method to develop a compression algorithm is then to build a statistical model of the source. Call it P theta sub theta of X. So this will be a surrogate in place of the true distribution. And then we can apply Huffman coding to this approximate distribution and use the code that we designed for this model, use that to compress the original source instead. So what are we looking at here? How should we design the statistical model? Again, the principle is to minimize the expected code length. And the objective function here is, again, this average of negative log probability of samples from the source under this statistical model. And we're trying to minimize this. But if you look at this and you get rid of the negative sign and you flip the minimum to maximum, this is exactly maximum likelihood estimation. And if you, as I write in this equation here, if you subtract the entropy of the source from this objective, which you might know as the cross entropy, you'll see that this is actually the KL divergence between the source distribution and our model's distribution. And because the KL divergence is always non-negative, we sort of recover the observation that the entropy is the fundamental limit of lossless compression. So basically the theoretical aspects of lossless compression have been worked out, and we have an efficient algorithm, Huffman coding, and a bunch of other algorithms that can kind of achieve that limit. But there are still some challenges associated with lossless compression, especially when the source is very high dimensional. For example, when you're looking at natural images, it has millions of pixels. So how do you design your statistical model for your source? We could start with something simple. So we could assume that our model distribution is fully factorized across all the dimensions of the source. But it's usually a bad idea. And instead, there are other ways of tackling this problem. So we could use the chain rule of probability and write down our model as a product, but with a conditional dependency here. So each coordinate is conditioned on all the coordinates before it. And this is without loss of generality. And there are models that do this. A familiar example might be the N-gram language model that uses this chain rule to break down a high dimensional estimation problem into just estimating these conditional probabilities. And there's also pixel RNN, pixel CNN for images. Another way you can tackle this problem is to use the sum rule of probability and express the source or the data distribution as a marginal distribution. We marginalize over some latent space. And this leads to another class of models called latent variable models, with the normalizing flow being a special case. And you'll need something else other than Huffman coding to deal with this marginalization problem, and it's called bit-spec coding, but we'll not get into that here. So this is kind of an overview of lossless compression and its more recent development. So people trying to come up with ways to model high-dimensional data and compress it. So now let's move on to lossy compression. And the motivation here are twofold. So one is if your data is truly continuous. So if you imagine if you have an analog signal, like audio wave, and you want to store it digitally. Well, the analog signal has sort of infinite entropy, if you think about it. If you want to capture a real value number, you'll need infinite number of bits to store that. So in this case, it's you'll have to lose some information in the original source. For example, I mentioned in the analog to digital conversion. But lossy compression is also sufficient for many applications, especially if we are the consumer of compression. So think about images and videos and audio. These are rarely coded perfectly. These are typically compressed in a lossy compression algorithm, but we don't notice it because these algorithms kind of cleverly exploit the limits of our perceptual system. And the big bonus, of course, is that by doing lossy compression, we can actually compress at a bit rate that is lower than the entropy of the source. So I'm going to just motivate this and walk you through kind of a classical problem of lossy compression, that is image compression. So as a bit of background, images are typically represented as this giant matrix of numbers, each number representing a brightness value for each pixel location. And these are typically 8-bit numbers, so they can take value from 0 to 255. And there's usually 3 channels to RGB to make up a color image. So you have 3 bits for each, 3 times 8 bits for each pixel. So if you just store this value, all these values of brightness naively, then you end up with actually really big image. So for example, if we have a picture or an image that has 3,000 pixels in each dimension, so it's a 9 megapixel image, and we're using 3 bytes for each pixel, then you're looking at 27 megabytes for this image if you just store it naively. Now, of course, what we do end up doing is to apply a lossy compression algorithm that kind of throws away some of the information, such that we end up with an image that is much smaller. So in the case of JPEG, you can get something that's like half a megabyte, and still look pretty good. So how do we get from 27 megabytes to 0.5 megabyte? A naive idea is to quantize each pixel independently. So by quantize, I mean to map one of 255 possible values into fewer possible values. So if we represent each brightness value, instead of using an 8-bit number, we use a 3-bit number, then we'll notice some degradation. But of course, we'll save some file size. And if we keep going, then if we reduce it down to 2-bit number, so each brightness value can be represented by only 4 values, then you can only get it down to by about 4.5 megabytes. And this, you can notice, I'm not sure if you can see via Zoom, but there's these artifacts, sort of granularity in these pixels. So these are artifacts that we can easily notice. So how does JPEG do this quantization, this throwing away of information, such that we don't really notice these kind of artifacts? So JPEG does something clever. What it does is it divides pixels into little blocks. It's actually not too important how you divide things into blocks, but so let's just go with this. So if we have 8x8 blocks, what JPEG does then is to apply what's called a discrete cosine transform. So it compares every one such little block with a whole array of possible frequency patterns. So going from left to right and top to bottom, we have these frequency patterns that have increasing frequency. So by comparing these little blocks to these bank of frequency patterns, we can extract how much frequency there is in each little block. So again, if we take just this on the left-hand side, some image that is represented in terms of brightness values, what DCT does is, again, compare these frequency patterns to extract another matrix such that each value represents the component in this filter, in this bank of filters, so how much frequency there is. And JPEG exploits this fact that for these numbers that correspond to the higher frequency components, we don't actually really notice any loss in these frequencies. So we don't really notice the sort of high frequency details in the images. So that when it quantizes this frequency information, it can do so with a coarser resolution. And for example, by setting a lot of these values to zeros. And afterwards, then it can apply lossless compression algorithm, such as the Huffman coding algorithm we already mentioned, to compress this stream of symbols furthermore. So this after that is just lossless compression. So this JPEG algorithm actually illustrates this idea of transform coding pretty well. So what this transform coding idea is really about is, it's given some image, we apply some algorithm, in this case the DCT algorithm, that infers or encodes some vector numbers, and then you apply rounding to this value, such that you end up with integer value symbols. After that, then you can apply lossless compression to these integer symbols and get a and perform lossless compression. And then the decoder can apply the inverse transform that I call G to get a reconstruction of the original image. And the principal goal of designing such a transform coding algorithm is to minimize this combination of two values. So you want to minimize the distortion that is incurred from this compression process. So in this case, I'm just taking the squared difference between the original image and the reconstructed image. You want to minimize the distortion and the rate. So here I should have written negative log p of z hat. So again, this z hat is the rounded value of these. You can think of as the frequency parameters, coefficients. And so you'll have to develop some model here that captures this frequencies of these sort of statistical regularities of these z hat, kind of like what we talked about with Huffman coding, to have an entropy model for these symbols. So you also want to minimize the average code length, or the rate, the bit rate of doing this compression at the lossless stage. So now, as a bit of an interlude, we'll look at something that seems completely unrelated, that is variational autoencoders and latent variable models. So what we're looking at here is a generative model for X from that we imagine is generated from some latent variable Z. And this generative model is typically trained by minimizing this negative elbow, or they're maximizing the elbow, which is this quantity here. So since this is a machine learning seminar, I assume you would be kind of familiar with this, how this works. Briefly, the inner portion of this negative elbow objective is measuring the KL divergence between the approximate posterior of latent variable given X and the true posterior. So this is on the right-hand side in this figure. It's basically capturing this inference process where you have an encoder that runs the X input, the data input, through some neural network that computes a posterior distribution over the latent variable. So this is Q of Z given X. So it's illustrated here. And whereas in the generative process, you kind of do the opposite. So you sample a data observation given a latent variable. So we'll see that this actually is really intimately connected to this transform coding paradigm. That is, if we look at a particular approximate posterior, if you use a posterior that has the form of a uniform distribution, so that the neural network given X computes sort of the mean of the posterior distribution, and this posterior distribution, like I said, can be represented as this posterior mean plus some uniform noise that is distributed between negative 0.5 and positive 0.5. If you use this particular choice of posterior, then you'll see that your negative elbow from this particular VAE looks a lot like the rate distortion objective I showed earlier with transform coding. So how this works is, again, like I already wrote here, is based on the reparameterization trick, where you, instead of sampling from the posterior of Z given X, you're sampling from this noise variable U, and you're rewriting the distribution of Q of Z given X in this form I just showed here, such that what you end up looking at is for the likelihood term, you'll end up with something that looks like a distortion. So, for example, if the likelihood is a Gaussian distribution, then if you take the negative log of the Gaussian likelihood, you end up with is a square distance between your observation and the predicted mean of this distribution. So how this predicted mean computed? Well, it's computed by decoding, so by applying this G function on a posterior sample. So a sample from the approximate posterior, like I said, is represented by this mean that's computed by the encoder network plus some noise. And similarly for the rate term, you can just replace a sample Z from the approximate posterior by a sample from this uniform noise distribution plus the mean that you compute with the encoder network. So this uniform noise essentially is representing a rounding process. So when you add uniform noise, you can think of this as rounding. So what you're doing here is perturbing the encoding with uniform noise. That is essentially simulating rounding this encoding to the nearest integer. And this allows you to train such a model with variational EM. So now with this in mind, what neural lossy compression does, or what we're trying to do is to learn a lossy compression algorithm with neural networks. So basically we can just replace the DCT and the inverse DCT components of JPEG with neural networks. So you want a encoder neural network that does the inference or the encoding, and you want a decoder neural network that does the generation. And again, you're trying to minimize this negative elbow that corresponds to the rate distortion objective of doing compression in this process. So now I'm going to go over my recent work and see how this idea of lossy compression and generative modeling kind of interplay, and how we can improve lossy compression with ideas from generative modeling. So this is work from Europe's last year. And I've already kind of given you an overview of how this particular form of variational autoencoder connects to lossy compression. And that is based on the similarity between these two equations here. So again, the negative elbow of an VAE, where you have a uniform noise distribution on the variational posterior, is basically approximating a rate distortion loss. So then this immediately leads us to the conclusion that if we can approximate the approximate posterior, or if we can do the encoding better, then we should be able to achieve better compression performance. So in this work, we actually proposed a bunch of stuff, but I'll keep it more basic and only mention or focus on the first two aspects of what we worked on. So again, the objective here is rather to think about the inference process of data compression. So notice that here I don't have an expectation over all the data samples. So this is for any given input X. We're trying to look at the rate distortion loss, or rather the compression loss under this particular trained model. So this is assuming we have already a model trained with variational EM, and we're trying to improve the inference at test time for any given input X. So the first idea is rather simple. So if we can actually optimize this compression loss directly over the encoding, so mu of z, what I wrote here is the output of the encoder network. If we can optimize it directly, then we should be able to do better than the naive encoding, which is computed by the encoder neural network. So this is done by just minimizing this negative elbow loss with respect to the parameters of the Q distribution, so this inference distribution. But another thing that we noticed is that we want to end up with ultimately is an integer valued encoding, because that's ultimately what we needed for lossless compression. So rather than just settling on some value that's continuous and rounding it later, we want to arrive at a value that's ultimately the best integer valued encoding. So we propose this algorithm called stochastic gumbo annealing that essentially does both. And so another view on this inference as compression problem is to think again about a probability model where you have a latent variable model that is a distribution over X and Z. So here I'm just writing down the joint distribution. And it's usually factorized in terms of a prior distribution over Z and a likelihood distribution of X given Z. And the problem here is that we we observe some data X, and we want to find the most likely value of Z that gave rise to X. So this is what's known as the map estimation problem. And you can pretty easily show that this is actually equivalent to trying to minimize the negative joint log likelihood. And again, by rewriting this objective, you can break it down into something that looks, again, like the rate distortion trade-off I mentioned earlier. So you have a term that measures the what's more similar to the rate term that I mentioned before. That is the cost of encoding the latent variable under some prior model, then plus some compression cost of X given Z. So again, if you think of this as a Gaussian distribution, you're looking again at some kind of squared error between X and the reconstructed version of X from the latent variable Z. So to simplify this discussion here, again, the goal to keep in mind is to come up with the optimal Z that minimizes this negative log join probability. I can actually simplify this problem a bit more and talk more generally about minimizing some function f of Z such that the Z belongs to a discrete set. So that's really the problem we're looking at. So it's the set of integer values. And if we think about the continuous case, if f is some function and the Z is just Rn, then you can just apply your favorite algorithm, say gradient descent, and come up with some value Z for the optimization problem. But in the discrete case, we can't really do gradient descent on this function because we have a discrete domain. So we end up doing, if you want to avoid a search problem that typically has exponential complexity, what we can do is to come up with a surrogate objective that kind of interpolates the value of the function on the Z space. So that's basically captured by this equation here. So there's a family of algorithms called variational optimization algorithms that essentially perturbs or rather convolves the objective function with a particular distribution that resembles kind of a variational posterior distribution. So this Q distribution of Z given some parameters that is unrestricted, so it can take values in Rn. And you can show that the surrogate objective, which now has value everywhere in terms of mu, it upper bounds the optimal value of the original optimization problem, where you optimize over all the discrete values of Z. So the basic idea is then to minimize the surrogate function in terms of mu and hopefully end up with something that we can ultimately round to a near value, to a nearest value of Z. So that is basically captured by the way we design this Q distribution. So the way we design this distribution is we propose it to be a categorical distribution that takes on a value that that is basically inversely proportional to the distance between where you are in terms of mu and a nearest value C that is in the search space. And we weigh this by a temperature tau, such that the closer the temperature is to 0, then the more uniform this distribution is. And if you increase this temperature towards infinity, then you'll eventually end up with a distribution that only places mass on the nearest neighbor of mu. So we apply this algorithm to improving the the encoding of lossy image compression. So again, this f function now is the rate distortion loss, or rather the negative log joint probability I mentioned earlier. And what we're trying to do is to go from this blue diamond, which is some initialization that is not necessarily integer valued, to find a integer value latent that minimizes the rate distortion loss. So we're able to do this pretty well and improve the lossy image compression performance significantly. At least it was in the new state of the art, at least at the time of our paper submission. So I'm not sure if you could see this over Zoom, because this video itself is being compressed. But what we're able to do is to take this image reconstruction that's from the baseline and run this algorithm and end up with a image that has more visual details. So there's like more wrinkles that is captured by the reconstruction, so that this image produced by our algorithm has lower rate distortion costs. So I actually realized I'm running out of time. So I'm going to skip the second part of the presentation that was about our HTML work. That gets fairly technical. So now let me just jump to the more recent work that I've been working on. So this work is concerned with what is the limit of lossy compression. So previously we kind of looked at kind of an existing paradigm where I try to push the limits of compression within that paradigm. So here I'm just looking at, given all the possible lossy compression algorithms, what is the best we can do? So the typical setup is, again, you have some data that you're trying to compress with some lossy compression algorithm. And the question is, what is the smallest file size on average that is needed by any lossy compression algorithm to make sure that you have a good enough reconstruction quality so that the compressed image doesn't look too different from the original image in some metric, such as, again, some kind of square error. And to be more precise, we can model the data distribution by a random variable x that takes value in some source alphabet, this set x, and the source induces a distribution. More precisely, it's a probability measure, p of x, on the source alphabet, and we have samples to this distribution that are IID random variables from this distribution. And we assume that there is a space Y that has the values, contains the values of all the possible lossy representations of X, so that the output of the lossy compression algorithm takes some value in this Y space. And we're given a function, a distortion function, rho, that looks at a pair of the original data and the reconstruction Y, and gives some number that is non-negative. It tells us how much these two differ. And again, the question is, what is the minimum number of bits you need on average to transmit the data samples with an average distortion that does not exceed some given threshold, capital D? Again, this is asking this question for any possible compression algorithm you can come up with. So this is, in some sense, a very fundamental question, and I'm not sure why these slides appeared again. But people have worked out this question a long time ago, again by Claude Shannon. There's a theorem that tells you, or maybe not a theorem, but a theory that tells you what is the minimum number of bits you need. So that is given by this function, what is called the rate distortion function. So again, back to our previous question, if I give you a distortion threshold D, that I want this lossy compression algorithm to stay below, then the minimum number of bits needed on average is given by this rate distortion function, evaluated at this threshold D. So this is the essence of the source coding theorem with the fidelity criterion by Shannon. And this magical function, this rate distortion function, has this elegant mathematical definition. It is minimizing some mutual information between x and y, such that the again, you have a threshold or a constraint on the distortion. So you want to search over all the possible distributions in the reproduction space. So distribution over the reproduction given the input that you can think of as identifying a lossy compression algorithm and trying to minimize the amount of information between the reconstructed data and the original data, again, subject to a distortion constraint. So conceptually, if you plot all the rate distortion performance in terms of the distortion and rate pairs of any hypothetical algorithm, what this rate distortion function does is that it separates those that are achievable by some lossy compression algorithm versus those that are not. So if you're above the RD curve, then this kind of rate distortion performance is theoretically possible. If you're below, then good luck. There's no way you can come up with a lossy compression algorithm that achieves this kind of rate distortion performance. But the problem with this definition is that we typically don't have a way to solve this problem analytically. So there's been a lot of efforts to compute this rate distortion function numerically. And there's quite some work based on computing an upper bound on this rate distortion function. So approaching this RD curve from above with an upper bound tells us what kind of performance is theoretically achievable by some kind of compression algorithm. But this is not very constructive. It doesn't tell us what kind of algorithm we can design, how we can design it efficiently to achieve performance that corresponds to this upper bound. So instead, we could also approach the RD curve from below. And any lower bound that we obtain would give us the performance ceiling of all the existing compression algorithms. So if we have an algorithm that is kind of close to this lower bound already, then it tells us that this algorithm is pretty close to optimal. So this is the approach I take. And this work that I'm currently working on is, as far as I know, a first attempt at developing this lower bound and approaching RD from below for the general case, where the alphabets, again, these are the sets that the data and the reproduction can take values in. These are arbitrary measurable spaces, whereas in previous work, these have to be finite sets. And the source distribution, P of X, can be any probability measure. So it can be discrete, continuous, it could be neither. So in the case of images, the source distribution is concentrated on some low dimensional manifold of Rn you can think of as having measure 0. So anyway, this P of X can be anything as long as we have IID samples for this distribution. So our work relies on this dual representation of the rate distortion function. So recall previously the rate distortion function is defined in terms of this constraint minimization problem. So it turns out that there's in some sense, a dual characterization of rate distortion function in terms of a maximization instead. So you're maximizing over a function g and some scalar, both need to be non-negative, of some expected value of negative log g. So again, it looks kind of like a cross entropy. And you want a constraint on the size of g. So you want G to satisfy, again, this inequality on this expectation for every value Y in the reproduction space. So basically, the takeaway message is that there is a maximization formulation of the rate distortion function that would allow us to obtain lower bounds by plugging in any G and lambda that satisfy this inequality here. And that's basically what we do. We try to maximize, again, this objective. If we do this over only a subset of functions, then we end up with a lower bound. So that's kind of the first sort of trivial observation. And that is, we can replace this set of all possible functions G by those that we can represent by a finite dimensional vector. So for example, a neural network parameterized by theta. And we can equivalently rewrite the constraint in terms of this supremum over Y of this expectation needs to be non-negative. And then we can basically apply a constraint optimization problem to algorithm to maximize this function of theta and lambda while trying to keep the constraint down to be non-positive. But of course, the catch here is that we don't actually know the analytical form of the objective function or the constraint because we don't know the source distribution. So we can't really compute these expectations analytically. So obviously, we don't have anything else to resort to but the samples. So we propose to approximate the objective by the Monte Carlo average of this thing inside the objective over samples. And this is straightforward because the objective function, again, this expectation here, we can just estimate this by the sample mean. And we have guarantees on how fast this converges by various laws and large numbers. But the constraint function is trickier. So it's the supremum over Y of another expectation, or to simplify the notation here. So some psi function that we're taking expectation to. So this is expectation parameterized by some Y. We're taking the supremum over Y, and what happens if we replace the expectation by the sample average, and then take the supremum? So it turns out this is more or less justifiable. Basically, this estimator that we developed here by maximizing a finite number of samples, we've shown theoretically that this is asymptotically unbiased, and the bias monotonically decreases with the number of samples. This is also strongly consistent, so it has guarantees on the exactness if you have infinite number of samples, of course. And we apply this algorithm to a two-dimensional Gaussian source and came up with a lower bound that is within 1 bit of the ground truth rate distortion function. It's, I guess, not super tight, but we're hoping to find ways to improve this so that we get closer to the rate distortion function. And here's some example visualization of how the neural network function evolves during this optimization. And it eventually converges to something that resembles the analytically optimal solution, G star, that sits above here. So with that, I'd like to conclude this presentation, and thank you for your attention. And let me know if you have any questions.
So let's thank Yibo for a very interesting talk. I think we have some echo here. This is certainly exciting work combining classical information theory ideas with modern neural networks. And exciting that it's happening here at UCI. Questions from the audience? Stephen, go ahead.
Yeah, thanks a lot for the talk. So,
somebody can somebody mute their mic? We're getting a lot of feedback here.
Okay, let me try it again. So one of the benefits of JPEG type compression algorithms is that they're really easy to run and not a lot of computational overhead. So could you compare the computational burdens of having to run a neural network every single time you need to compress an image, say, or what are some applications where that cost would be worth it?
Yeah, great question. So JPEG is probably 2 orders of magnitude faster than anything you do with a neural network, at least nowadays. So yeah, that's a very, very valid concern about the computational viability of using these neural networks for compression. And so I guess the main argument is that at this stage, we're still kind of exploring the potential of deep learning for compression. So we haven't really looked into the computational aspects that much. So we're just pushing this rate distortion performance currently. And these deep learning methods are able to significantly outperform JPEG in terms of rate distortion. So in terms of, yeah, like this PSNR metric for images, they're typically like 3 to 5 above the JPEG performance. So if you really want optimal compression performance, then yeah, the deep learning algorithms might be your choice. But if you want something that's fast and flexible, maybe you still want to stay with JPEG. But I'm optimistic that with more research in neural network compression and ways to speed up these deep neural networks, I think there are yeah, a lot of potential to make the neural methods more competitive with JPEG in terms of computation.
Thank you.
Mm-hmm.
Other questions for Yibo? Yibo, I'll ask a quick question. In terms of when you go to a lot of compression, a lot of loss, say for images or audio, do the distortion measures map to human perception well? You know, what a human perceives in terms of one compressed image or another.
Mm-hmm. So if I understood the question is, how do you design a distortion so that it aligns with human perception better? Yeah, so sort of kind of as a interesting example, the neural methods already are able to do this kind of implicitly. So without us telling how it should, how it should come up with the reconstruction. So, so here's the reconstruction with JPEG at a fairly low bit rate. And here's an example with like a deep learning based method at the same file size. And keep in mind that this algorithm is based on minimizing mean square error distortion. And it's able to already avoid these blocky artifacts from JPEG. So, so that's a nice bonus we get from these deep learning algorithms. It's able to somewhat produce more reconstruction that are some more semantically meaningful and preserve details in a more visually pleasing way. But then there's also separate research on how to design this reconstruction or the distortion function. So yeah, I don't think I have the slide here, but yeah, essentially it's this row function. And there are information theoretic criteria you can look at. I think there's work on this, I think last year's NeurIPS, on how to optimize this row. But again, there's, again, this kind of based on samples and trying to minimize or maximize some mutual information. But it hasn't really shown, I don't think, any empirical result. So it's more theoretical work at this stage. Yeah, hopefully that answers your question.
Thanks, Yibo. Any other questions for Yibo?
Yeah, I just had a comment on the Gumbel, when you're talking about the Gumbel distribution, like a Gibbs measure. I think the temperature, if I recall, as temperature goes to 0, the mass concentrates on a single value. As temperature goes to infinity, if that tau was your temperature goes to infinity, the exponent goes to 0, and it flattens the exponential out into a uniform. Did I miss something? I think you were saying it was the other way around. Was that tau actually an inverse temperature, or did I confuse that?
Right. So here, right, as you decrease the tau, yeah, I think I may have made a mistake here. So tau towards 0 should be more deterministic.
That's right.
So, that's right. Yeah. I think I had an outdated version of the slide.
Yeah, okay. No, I make mistakes like that. I do the same thing, and I talk about temperatures all the time. I always have to think about them.
Right. So this should be
I didn't get it wrong.
This should be the corrected slide. So yeah, I had a visualization for decreasing temperature and the
that's it. Lower, more deterministic. Yeah,
right.
Okay. Gotcha.
Yeah.
Thank you.
Yep.
Since we've gone past 2 p.m. and we're getting a lot of echo, let's call it a day. Thank Yibo for a very interesting talk, and we'll see you back here next week. So let's thank Yibo again. All right, bye everybody.